What if I told you that in 1973, a Louisiana drag racer figured out how to make a transmission shift faster than you can blink? We're talking 0.08 seconds. That's 8/100ths of a second, the time it takes a hummingbird to flap its wings once. And this wasn't some million-dollar factory program with unlimited resources and teams of engineers. This was one guy in his garage with a die grinder and an idea that Chrysler's engineers said was impossible. Look, before we get into this, I need to set the scene for you properly because the context is everything. This is legacy motoring, and I spend way too much time thinking about how a single person with the right idea can outperform an entire corporation full of engineers. If you're someone who obsesses over the mechanical ingenuity behind drag racing and the unsung heroes who changed automotive history forever, make sure to hit the subscribe button and give this video a thumbs up if this helps you out. Now picture this. It's a humid Saturday night at a Louisiana drag strip in 1973. The air is thick with tire smoke and racing fuel. Mosquitoes are swarming under the tower lights, and the bleachers are packed with locals who've been coming to this strip every weekend since they were old enough to climb out of the back seat. In the staging lanes, a Plymouth Duster pulls forward. Nothing special about the exterior, same fiberglass hood, same slicks, same roll cage as every other superstock car lined up behind it. But when the Christmas tree drops and that Duster launches, something is different. Something the crowd can feel in their chest before their brains even register what happened. The shifts happen so fast that nobody in the stands can even process them. By the time competitors are grabbing second gear, this car is already pulling hard in third. The time slip comes back, and it shows a 0.4 of a second advantage that shouldn't exist. Not in superstock racing, not with a supposedly stock transmission, not with the same engine package everyone else is running. The driver's name was Herb McCandless. His secret was a modified TorqueFlite valve body that shifted faster than anything Chrysler ever imagined was possible. And this is the story of how one racer outsmarted one of Detroit's big three by taking their street transmission and turning it into a drag racing weapon that broke the accepted laws of hydraulic physics. McCandless didn't just modify a transmission, he revolutionized automatic drag racing and created technology that Chrysler themselves would later try to replicate and sell through their own parts catalog. Here's what most people don't realize about the TorqueFlite transmission. To understand why McCandless's achievement was so revolutionary, we need to travel back to 1962, when Chrysler introduced this thing to the world. This wasn't just another automatic slush box. Chrysler engineers designed the TorqueFlite as the ultimate street transmission, smooth, reliable, and virtually indestructible. While GM was having issues with their transmissions cracking cases, and Ford was still refining their C-Series units, Chrysler's A727 TorqueFlite was built like a bank vault. It used a Simpson planetary gear set with a unique valve body that controlled hydraulic pressure through precisely machined passages. Think of those passages like the veins and arteries in your body. Every one of them was a specific diameter for a specific reason. These passages were intentionally restricted, deliberately choked down to create smooth, comfortable shifts that wouldn't jolt your grandmother in the passenger seat or strain driveline components during normal driving. The valve body itself was the brain of the entire operation. Think of it as a hydraulic computer, built decades before microprocessors were cheap enough to put in cars. It directed fluid pressure to different clutch packs and bands to create gear changes, and it did this purely through mechanical means. Springs, ball checks, calibrated orifices, and precisely machined spool valves, all working together in a symphony of fluid dynamics. Chrysler's engineers spent thousands of hours perfecting the passage sizes, the spring rates, and the check ball locations to achieve shifts that took about 0.5 seconds to 0.7 of a second to complete. For street driving, this was absolutely perfect. You could hand your keys to anyone and they'd comment on how smooth the transmission felt. But for drag racing, that 0.5 second shift time was death. Pure, measurable, unavoidable death. Now, you might be thinking, 0.5 second doesn't sound like much. Who cares about 0.5 second? Here's where the math gets brutal. In superstock drag racing, you're typically making 2 full throttle shifts during a quarter-mile pass. If each shift takes 0.5 second and your competitor's shifts take a 1/4 second, you've lost 0.5 second total. In a class where the margin of victory is regularly 0.02 of a second, losing 0.5 second is like showing up to a knife fight with a pool noodle. You're not just losing, you're not even competitive. By 1973, the drag racing landscape had evolved into a game of milliseconds. Superstock racing in particular had become incredibly competitive. These were supposedly stock cars running factory engines and transmissions, but everyone was pushing the rules to their absolute breaking point. Weight reduction was maxed out. Engines were blueprinted within an inch of their lives, with every bearing clearance optimized and every port matched. Suspension geometry was dialed down to fractions of degrees using techniques borrowed from professional chassis builders. The only frontier left, the only place where significant time could still be found, was the transmission. And here's where Herb McCandless enters our story in a way that would change everything. McCandless wasn't some weekend warrior who stumbled onto something by accident. He was a professional racer who had been campaigning Mopar products since the mid-1960s, back when the muscle car wars were at their peak, and Chrysler was sending factory-backed cars to drag strips across the country. He'd driven Hemi Darts, run superstock Barracudas, and earned a reputation as one of the most technically minded racers on the East Coast circuit. He understood something that a lot of drivers never fully grasped. In superstock racing, where engines were limited by strict class rules and everyone was running essentially the same cubic inches with the same compression ratios, the transmission became the ultimate difference maker. Every tenth of a second lost during a shift was a tenth you could never get back. You couldn't make it up anywhere else. The engine wasn't going to suddenly find more horsepower between the 60-foot mark and the finish line. The car wasn't going to magically get lighter during the run. Whatever time you left on the table during those 2 gear changes was gone forever. McCandless had already tried everything the aftermarket had to offer. Shift kits from B&M Racing and TCI Automotive helped, no question about it. They typically modified the valve body with stiffer springs and different check ball arrangements that dropped shift times to about 0.3 of a second. That was a significant improvement over stock, and for most racers it was enough. Manual valve bodies eliminated the automatic shifting entirely, putting full control in the driver's hands through a ratchet shifter. But even with manual control, the shifts themselves were still too slow. The problem, McCandless realized, wasn't about when the shift happened, it was about how fast the shift happened once it started. The control wasn't the bottleneck, the hydraulic flow itself was the bottleneck. The passages in the stock valve body were simply too small, too restrictive to move enough fluid fast enough to slam those clutch packs together in the time frame he needed. It was like trying to fill a swimming pool through a garden hose. You could turn the faucet on faster, you could increase the water pressure, but until you got a bigger hose, you were never going to fill that pool in the time you wanted. So McCandless did something radical, something that every transmission rebuilder he talked to said was crazy, something that Chrysler's own engineers would later say violated fundamental hydraulic principles. He took a valve body and started cutting. Using a die grinder fitted with an assortment of carbide burrs, the kind of tools you'd normally use for porting cylinder heads, McCandless began enlarging the hydraulic passages inside the valve body. But here's the thing, this wasn't random hacking. This wasn't some guy going at a precision machine's part with reckless abandon. Each passage had to be enlarged to a specific dimension. Too big and you'd lose the pressure you needed to actually engage the clutch packs. The fluid would just flow through without building enough force to clamp the plates together. Too small and you gained nothing, just wasted time and ruined a perfectly good valve body. The separator plate between the valve body halves needed modification too. Stock separator plates used calibrated orifices, tiny holes drilled to exact sizes to control and meter fluid flow between different hydraulic circuits. McCandless drilled these out to specific sizes he determined through countless trial and error runs at the track. Some holes got bigger, some got blocked off entirely, some got relocated to positions that weren't in Chrysler's original engineering drawings. The spring modifications were equally critical. The stock valve body used springs with specific rates, carefully chosen by Chrysler's engineers to cushion the movement of shift valves and provide smooth gear transitions. McCandless replaced these with much stiffer springs that would snap the valves into position instantly, like a mousetrap instead of a screen door closer. He removed check balls that Chrysler had placed at strategic intersections to soften the pressure pulses during shifts. He eliminated accumulator pistons, those hydraulic shock absorbers that stored pressure momentarily and released it gradually to smooth out gear changes. Every single element that Chrysler had engineered for comfort, every design feature that made the TorqueFlite the smoothest shifting automatic on the road, McCandless ripped out in the name of speed. But this is where it gets really interesting. McCandless discovered through painful experience that simply making everything bigger and stiffer wasn't enough. The hydraulic circuits within the valve body didn't operate independently. They were interconnected in ways that weren't immediately obvious. When you increased flow in one passage, it affected pressure in others. When you changed the spring rate on one valve, it altered the timing of events happening elsewhere in the system. The entire valve body was an ecosystem, and changing one variable changed everything. The timing of shift overlap, that split second when both gears are partially engaged during a transition, had to be reduced to almost zero. In a stock TorqueFlite, this overlap lasted a few tenths of a second, providing a smooth handoff between gears. McCandless needed to cut it down to almost zero. But here's the danger. Too much overlap and you'd burn up the clutch packs in a matter of runs, because both gears would be fighting each other. Too little overlap and you'd get a momentary neutral condition, followed by a brutal driveline shock when the next gear slammed in. That shock could snap axle shafts, explode U-joints, twist drive shafts, and destroy ring and pinion gears. McCandless was trying to thread a needle while riding a mechanical bull. The first full power test of McCandless's modified valve body nearly destroyed his race car. He staged the Duster, brought the engine up to launch RPM, and released the trans brake. The car left the line hard and climbed through first gear. When the shift from first to second happened, it was unlike anything he'd ever experienced. The shift happened so violently that it twisted the drive shaft like a pretzel. The U-joints exploded, sending chunks of hardened steel bouncing off the underside of the car. The transmission mount ripped clean off the crossmember from the instantaneous torque transfer. McCandless coasted to a stop at the end of the track, got out, looked underneath, and saw the carnage. But then he looked at the data. The shift had taken 0.08 seconds, 0.08 of a second. Let me put that in perspective for you. A human blink takes about 0.1 to 0.4 seconds. McCandless's transmission had completed an entire gear change faster than you could close your eyes. If you were watching the tachometer during that shift, you literally would not have seen the needle move because your eyelids would have been too slow to catch it. The mechanical violence was incredible, but the result was undeniable. During that shift, the transmission went from one gear to the next with no perceptible interruption in power delivery. The tachometer needle didn't even have time to drop. It was essentially a seamless transfer of torque from one gear ratio to another, happening so fast that the engine never had a chance to flare or lose momentum. It was, for all practical purposes, a seamless power band that shouldn't have been possible with 1970s hydraulic technology. Here's the thing most people miss about this achievement. McCandless wasn't working with electronic solenoids or computer-controlled actuators. He was doing this with pressurized fluid flowing through machined passages. Every shift was initiated and completed purely through hydraulic force, controlled by mechanical valves and springs. The precision required to make this work was staggering. McCandless spent the next several weeks reinforcing everything behind that transmission, because it turned out that while the TorqueFlite itself could handle the abuse, nothing in the driveline was designed for shifts this violent. The drive shaft was replaced with a custom unit made from thicker DOM tubing, the kind of heavy wall seamless steel that you'd normally see in roll cage construction. He sourced heavy-duty U-joints rated for twice the torque capacity of the stock units, and had them balanced as an assembly to prevent vibration at high RPM. A transmission blanket made from ballistic nylon was wrapped around the case to contain the carnage if something inside decided to let go at 7,000 RPM. The transmission mount was reinforced with additional steel plating welded directly to the crossmember, spreading the load over a wider area so the instantaneous torque pulses wouldn't rip the mount free again. Even the rear axle needed serious attention. The instant application of torque during those brutal shifts was trying to wrap the leaf springs into an S shape, a phenomenon called axle wrap that could unload the tires and break traction at the worst possible moment. McCandless added traction bars, reinforced the spring perches, and upgraded to a set of axle shafts made from stronger alloy steel. But when McCandless showed up at the next race with everything properly reinforced, the results were absolutely devastating for the competition. His Duster would leave the starting line like everyone else, same 60-foot times, same launch, nothing suspicious about the way it left. But by the time the other cars in the class were completing their first gear change, that smooth 0.3 of a second shift that the aftermarket kits provided, McCandless was already accelerating hard in second gear, pulling away with an advantage that grew with every foot of racetrack. The advantage compounded with each shift. First to second, 0.08 seconds versus the competition's 0.3 seconds. That's a 0.22 second advantage on just one shift. Second to third, another 0.22 seconds. Total shift time advantage over a quarter-mile pass, nearly half a second. In a form of racing where victories were measured in hundredths of a second, where you might run 8 rounds of eliminations and win every round by 2 or 3 hundredths, McCandless had found nearly half a second just in transmission efficiency. He hadn't touched the engine, hadn't changed the gearing, hadn't lost any weight. He simply made the transmission do its job faster than anyone thought possible. The competition was completely baffled. They could hear something was different. McCandless's car made a distinctive sharp crack sound during shifts instead of the usual whoosh of a normal automatic engaging a gear. It sounded almost like a gunshot under the car, a violent mechanical bark that was completely unlike anything they'd heard from a TorqueFlite before. Some competitors thought he was running a Liberty clutchless manual transmission that had been painted and disguised to look like a TorqueFlite. That was a serious accusation in superstock racing, where running non-stock components was grounds for disqualification and suspension. Others accused them of using nitrous oxide, saying there was no way a naturally aspirated engine with a stock transmission could put up those numbers. A few even suggested he'd somehow modified the engine beyond class legal specifications and was just using the transmission noise as a distraction. The tech inspectors came after him hard. They tore his car apart at multiple events, going through the engine with measuring tools, checking bore sizes, compression ratios, camshaft specifications. They weighed the car down to the ounce. They inspected the exhaust system for hidden bottles, and every single time, they found nothing illegal. The transmission was a genuine Chrysler TorqueFlite. The valve body was a genuine Chrysler casting. There was no rule in any sanctioning body's rulebook that specified how fast a transmission had to shift. Nobody had ever thought to write that rule, because nobody had ever imagined someone would figure out how to make an automatic shift this fast. Now, you might be thinking, well, once people figured out it was the valve body, couldn't they just copy what he did? And sure, eventually they tried. But here's what most people don't realize about precision machining work done with hand tools. It's an art as much as a science. McCandless had spent hundreds of hours developing his modifications through trial and error. He knew exactly which passages needed to be enlarged and by how much. He knew which orifices in the separator plate needed to be drilled out and which ones needed to be left alone or blocked entirely. He knew the exact spring rates that would produce the fastest shifts without causing hydraulic lock or pressure loss. All of that knowledge was in his hands and in his head. There were no blueprints, no specification sheets, no YouTube tutorials. Word of McCandless's secret weapon spread through the Mopar racing community like wildfire anyway. Racers from across the country reached out, offering him thousands of dollars for one of his modified valve bodies. And McCandless, being a practical man who recognized an opportunity, began building valve bodies for select customers who agreed not to reveal his techniques or allow anyone to disassemble and reverse engineer the modifications. Each valve body was hand-modified, a process that took dozens of painstaking hours to complete. But passages had to be enlarged with surgical precision using carbide burrs that wore out quickly and had to be replaced frequently to maintain consistent cutting dimensions. One slip of the die grinder, one moment of lost concentration, and the valve body was scrap. You couldn't weld up an aluminum casting and remachine it. If you cut too deep or in the wrong direction, you threw that valve body in the trash and started over with a new one. Let me talk about the technical aspects because they deserve a deeper examination. In a stock TorqueFlite, the 1-to-2 shift worked like this. The transmission control system would sense engine speed and throttle position through the governor and throttle pressure circuits. When conditions were met for an upshift, hydraulic pressure would gradually release the rear band while simultaneously applying the front clutch pack. This overlap period, lasting about half a second, ensured smooth power transfer between gear ratios. The engine speed would drop slightly during the transition, the car would settle momentarily, and then acceleration would resume in the new gear. It felt seamless from the driver's seat, and that was exactly what Chrysler intended. McCandless reduced this entire sequence to 0.08 seconds by dramatically increasing the exhaust rate of the rear band servo while simultaneously slamming the front clutch on with maximum available pressure. There was virtually no overlap period. The band released, the clutch engaged, and the gear change was complete before the engine crankshaft had time to complete a single revolution at the shift point. The hydraulic pressure in a stock TorqueFlite ran about 90 to 130 psi, depending on throttle position and engine speed. At light throttle, pressure was low for smooth shifts. At wide open throttle, pressure increased for firmer shifts, but Chrysler still kept it moderate to protect driveline components. McCandless's modifications pushed line pressure to over 200 psi at wide open throttle. Some of his later valve bodies reportedly generated pressure spikes approaching 300 psi momentarily during the shift event itself. The clutch packs, originally designed for gradual progressive engagement, were now being hammered together with tremendous force. Stock Chrysler clutch plates had grooves machined into their friction surfaces, channels that allowed transmission fluid to escape slowly during engagement. This created a brief period of controlled slip that cushioned the transition. McCandless ran smooth friction plates with no grooves, plates that grabbed the instant they made contact. The friction materials were upgraded from the stock organic compounds to sintered metallic materials that could handle the dramatically increased heat and clamping pressure without glazing or disintegrating. The separator plate modifications were equally crucial to making the whole system work. Stock separator plates use precisely sized orifices, typically ranging from 0.093 inches to 0.125 inches in diameter, to meter fluid flow between the various hydraulic circuits. These tiny holes acted like traffic cops, controlling how fast fluid could move from one part of the valve body to another. McCandless enlarged critical orifices to as much as 0.250 inches in diameter, effectively doubling or tripling the flow capacity in areas where speed mattered most. But he also discovered something counterintuitive. Some passages actually needed to remain restricted or even be made smaller than stock to maintain proper pressure balance throughout the system. It was like tuning a carburetor. You couldn't just drill out every jet to the maximum size and expect more power. Some circuits needed more flow, others needed less, and finding the right combination was a delicate dance of fluid dynamics that took McCandless years to perfect through thousands of test passes. The spring modifications went far beyond simply installing stiffer hardware. Stock valve body springs typically range from 15 to 20 pounds of force. McCandless increased spring pressure to over 40 pounds in some applications, using custom wound springs that he sourced from industrial suppliers rather than automotive parts companies. These stiffer springs forced the shift valves to snap into their new position instead of sliding gradually through their bore. The difference was like the difference between slowly pushing a door closed and kicking it shut. Both get the door closed, but one does it a whole lot faster. The governor valve, which controlled shift points based on vehicle speed, was modified to hold gears longer so McCandless could shift at precisely the RPM where his engine made maximum power. In stock form, the governor would trigger an upshift based on a predetermined relationship between vehicle speed and throttle position. McCandless recalibrated this by changing governor weights and springs, so the transmission would hold each gear deeper into the power band before shifting. Combined with the instantaneous shift speed, this meant the engine was always operating at peak output, never wasting time accelerating through RPM ranges where power fell off. But the real genius, the modification that separated McCandless from everyone else who was trying to speed up their shifts, was the accumulator delete. Chrysler used accumulator pistons as hydraulic shock absorbers inside the valve body. During a shift event, some of the hydraulic pressure that should have been going directly to the clutch pack was instead diverted through a side circuit to compress an accumulator piston against a spring. This absorbed the initial pressure spike and released it gradually, dramatically softening the gear change. It was brilliant engineering for a street car. For a race car, it was like putting a pillow between a hammer and a nail. McCandless blocked off the accumulator circuits entirely. He plugged the feed holes, eliminated the pistons, and redirected all available hydraulic pressure straight to the clutch packs, with nothing to absorb or soften the impact. This single modification was responsible for a significant portion of the shift speed improvement. Without the accumulator stealing pressure and cushioning the engagement, every ounce of hydraulic force went directly to clamping those clutch plates together as fast as the fluid could physically get there. This is where it gets really interesting from a durability standpoint. A stock TorqueFlite, driven normally, could easily run 100,000 miles or more between rebuilds. Chrysler had engineered so much margin into the design that taxi companies and police departments relied on them for hard service duty. McCandless's race-modified units needed fresh clutch packs every 50 to 75 passes down the drag strip. The bands would wear visible grooves into the drums from the violent engagement forces. The pump, which was never designed to sustain pressures above 150 psi for more than brief moments, would begin to cavitate from the extreme pressure demands, creating tiny vapor bubbles in the fluid that eroded the pump gears over time. Seals would harden and crack from the heat generated by the violent shifts. But in drag racing, durability meant lasting one season, not 10 years. A quarter-mile pass takes about 10 seconds. 75 passes represented roughly 12 minutes of total operating time spread across an entire racing season. The performance gain easily justified the maintenance schedule, especially when you are winning rounds and collecting prize money. Chrysler's engineers eventually caught wind of what McCandless was doing out there in Louisiana. In 1974, a team of transmission specialists from Chrysler's engineering headquarters at Highland Park, Michigan, made the trip south to visit his shop. What they found astounded them. Here were modifications that violated virtually every design principle they'd been taught. The shifts were too fast. The pressures were too high. The mechanical stress on every component exceeded the published engineering specifications by factors of 2 or 3. One Chrysler engineer, after watching McCandless's car make a pass and reviewing the data, reportedly shook his head and said something to the effect of, "This shouldn't work. You're asking the hydraulic fluid to move faster than physics should allow through passages this size. The pressure differential should be causing cavitation damage within a dozen passes." But it did work. The valve body was still functioning after hundreds of passes. The shifts were still consistently in the 0.08 second range, and Chrysler wanted in on it. By 1975, Chrysler's Direct Connection Performance Parts Catalog, their in-house speed parts division that catered to racers, offered what they called a super stock valve body that incorporated many of McCandless's core modifications. Wider passages, stiffer springs, eliminated accumulators, modified separator plates. The factory version was engineered with Chrysler's usual thoroughness and built on proper production tooling rather than hand-ground with carbide burrs. But it was conservative compared to McCandless's full race units. Chrysler couldn't sell something that violent to the general public, even through a performance parts catalog. Liability concerns meant they had to soften the shift slightly. Their version brought shift times down to about 0.15 seconds, still impressively fast, still faster than anything else available from GM or Ford's racing programs, but not McCandless fast. The competition gap remained, just smaller than before. The impact on superstock racing was immediate and lasting. Within 2 years of McCandless proving what was possible, every serious Mopar racer was running some version of a modified valve body. The technology crossed manufacturer lines too. GM racers looked at what McCandless had achieved with the TorqueFlite and began applying similar principles to the Turbo 400. Ford's C6 transmission got the same treatment from innovative builders on the blue oval side of the fence. But the TorqueFlite remained king of the drag racing transmissions because its robust aluminum case, its beefy planetary gear set, and its oversized clutch packs were simply better suited to the extreme modifications than anything else on the market. McCandless continued refining his valve body work through the late 1970s with an almost obsessive dedication. He discovered that different engine and vehicle combinations required different valve body calibrations. A small block 340-powered car needed different shift characteristics than a 440 wedge car, which needed something different again from a Hemi-powered combination. The torque curves were different, the RPM ranges were different, the weight of the rotating assemblies affected how quickly the engine responded to load changes. Each combination required custom tuning of passage sizes, spring rates, and separator plate orifice dimensions. By 1978, McCandless had developed over 20 different valve body specifications, covering virtually every Mopar racing application, from lightweight A-body superstockers to heavy B-body sedans running modified production classes. His notebooks, filled with hand-drawn diagrams and cryptic numerical notations, represented a body of knowledge that existed nowhere else in the world. The economic impact of his work was significant. McCandless was reportedly charging between $500 and $800 for a fully modified valve body in 1975. Adjusted for inflation, that's roughly $2,500 to $4,000 in today's money. For a professional racer who stood to win or lose thousands in prize money over a season, it was a bargain investment. McCandless built hundreds of these valve bodies during the 1970s, establishing a cottage industry that still exists today in the form of companies that specialize in high-performance TorqueFlite modifications. The technical evolution continued into the 1980s. Trans-brake technology, which locked the transmission in both first gear and reverse simultaneously to allow the engine to build boost or RPM against a converter before launching, required even more precise valve body modifications. McCandless pioneered passage configurations that could handle the extreme pressures generated during trans-brake operation without bleeding off pressure to other circuits. When electronic shift solenoids began replacing manual shift linkages in racing applications, McCandless adapted his designs to accommodate the new hardware while maintaining the hydraulic flow advantages he'd spent a decade developing. Modern drag racing transmissions owe everything to what McCandless figured out in that Louisiana shop. Today's competition power glides and turbo 400s used in professional drag racing can shift in under 0.05 seconds, even faster than McCandless's original 0.08 second achievement. The valve bodies in those transmissions are CNC machined to tolerances that McCandless could only have dreamed of, cut on computer-controlled equipment that can hold dimensions within a tenth of a thousandth of an inch. But the fundamental principles remain exactly the same. Maximize hydraulic flow through critical passages, minimize shift overlap between gears, eliminate every cushioning device that slows down the engagement. Every pro stock car running down the quarter mile today uses technology whose DNA traces directly back to McCandless. The human element of this story is what makes it truly compelling. McCandless wasn't a trained engineer. He didn't have a degree in fluid dynamics or mechanical engineering. He was a racer who understood transmissions through hands-on experience rather than equations and computer models. His modifications were developed through thousands of hours of trial and error, not finite element analysis or computational fluid dynamic simulations. When something broke, he examined the failure, figured out why it happened, and engineered a solution. When a modification showed promise, he refined it incrementally through dozens of iterations. It was pure empirical engineering at its finest, the same approach that built the hot rod industry from the ground up. The safety implications of McCandless's work extended beyond his own car. A transmission exploding at 7,000 RPM could send shrapnel through the floor pan with enough force to seriously injure or kill a driver. McCandless witnessed several close calls in his career where failed transmissions nearly caused catastrophic injuries. He became one of the earliest and most vocal advocates for mandatory transmission blankets in superstock racing, lobbying the NHRA and other sanctioning bodies to require this safety equipment. The NHRA eventually made transmission blankets mandatory for certain classes, and while McCandless wasn't the only voice pushing for the change, his first-hand experience with the forces involved added significant credibility to the argument. By the end of the 1970s, McCandless's influence extended far beyond valve bodies. He consulted with transmission case manufacturers about designing stronger housings. He worked with clutch material suppliers to develop friction compounds specifically optimized for the extreme engagement forces his valve bodies produced. He collaborated with transmission fluid companies on developing racing-specific formulations that could handle higher operating temperatures and maintain viscosity under the extreme shear forces generated during those violent shifts. Today, McCandless's original hand-modified valve bodies are collector's items. Mopar enthusiasts who understand their historical significance will pay thousands of dollars for an authenticated McCandless valve body, not necessarily to race with, but to own a piece of drag racing history. But their true value was never monetary. They represent something more fundamental about innovation and the human spirit. They represent a moment when one racer looked at what an entire corporation full of brilliant engineers had declared was the limit of hydraulic performance and said, "Watch this." In 0.08 seconds, he proved them wrong and changed the trajectory of automatic transmission performance forever. Look, the philosophical lesson here is profound, and it applies far beyond drag racing. McCandless proved that factory engineers, as brilliant and well-resourced as they are, designed for compromise. Street transmissions need to be smooth, quiet, durable, and compatible with every driving style, from a teenager learning to drive to an elderly person running errands. Racing transmissions need to do one thing and one thing only: shift as fast as physically possible. By stripping away every compromise, McCandless created something pure, a transmission that did one thing perfectly instead of many things adequately. What revolutionary modification have you seen that completely transformed the vehicle's performance? Drop a comment below and share your favorite story of grassroots innovation beating factory engineering. If you enjoyed this deep dive into transmission technology and racing history, subscribe for more stories of the innovators who pushed automotive performance beyond what anyone thought possible. Until next time, keep those shifts quick and those times dropping.